But before we talk about logarithms, we're going to talk about exponential functions. And I wrote most of this for you, which is so nice. Normally I don't print these out for students. Exponential functions are called transcendental functions, meaning that they're not really very nice numbers. And think about before people all had scientific calculators, doing things like logarithms, working with pi, working with square roots, wasn't really that much fun to do because people had to figure those things by hand. Even when I was in school back in the 90s, in the textbook, in the back of the textbook, there were log tables, which means you couldn't just type on your calculator to get a log decimal, because not everyone had calculators. And so in the back of the book, they had these tables, and that's what you went to find your decimal approximations, is you had to go to the table and do it. And I always had a scientific calculator, but I remember my teacher still made us use these tables, because that's what they used in the 80s, if they all used those tables, and in the 70s. And if you talk to your parents talking about trig tables or log tables, they probably all remember getting this sheet in the back of their book that you had to go and find the decimal. So in not such a long time, we've come a long way. We don't use log tables anymore. But transcendental, that's kind of a word that doesn't come up very often. Pi is a transcendental number. Exponential and logarithmic functions are transcendental functions, meaning that they're not very nice answers. They're not the solution of a polynomial equation with integer coefficients. All right? So exponential function, if we write it with base b, this is kind of our function here. F of x equals a times b to the x, and then I left some blanks for you to fill in. So what does that mean? A is non-zero, because if a were 0, then it would all equal 0. Notice it says b is positive, and we'll talk about in a minute what if b was negative. But b is positive. B can't equal 1, because 1 to any power is 1. That's not going to be an exponential function. And x is a real number. So x could be anything. We don't usually like graphing like something to a terrible power, but really x could be a rational number or an irrational number. And then we say that the constant a is the initial value of f, and b is the base. I'm just going to write that up there again, this formula. F of x equals a times b to the x. Sometimes writing it all printed out. Right? So a is the initial value. Think about what that word initial means. It means like the starting value. If you remember stuff from last year, or maybe just stuff from chemistry class, talking about exponential growth, exponential decay, especially in chemistry, how much you start with, right? That should be the a value, and then b is your base. Sometimes we call b the growth factor or the decay factor, depending on the problem that we're talking about. All right? This book pretty much starts over with logarithms. It doesn't really assume that you know a lot. So some of the problems today are just practicing solving exponential functions. And so these first couple here just say evaluate each function to the nearest thousandths. Decimal answers mean that we're approximating, which means you need to round to what the directions always say to round to. On the test, I will always tell you what to round to, and it's important that you round correctly. So you want to practice using the calculator that you're going to use, I think, on the test. So if you use one of my calculators, over the next few days, a pretty good habit is to just come in and grab a calculator, because we're going to use calculators a lot in this chapter. You want to always make sure that you get the same answer that I get. And so on this one, right, it says evaluate. So I could just plug in f of negative 2 would be 3 to the negative 2 power. Without a calculator, we could figure this one out, right? It's not so bad. What does it mean to have a negative exponent? Move it down. So that's really the same as just 1 over 3 squared, which means this one you could give an exact answer. It's just 1/9. But you can also type that in your calculator. And on my calculators, the caret button, right? The caret button is what you're going to do to take something to a power. If you're putting more than just one number up there, you want to put it in parentheses, so that way it knows what to do. But you should get like 0.1 repeating. Did you get 0.1 repeating when you did this? And the nearest thousandths is how many decimal places? Tenths, hundredths, thousandths. 3 decimal places. And usually we go 3 decimal places. Sometimes it'll say the nearest hundredth. If it doesn't say what to round to, I would say 2 or 3 is kind of what the norm would be. But on a test, if it doesn't say, and I don't say, hey, round to this, I can't mark you wrong for not rounding to the right number of decimals. But usually you want to be accurate. On the AP Calculus exam, if you plan to take AP Calculus next year, you have to go to 3 decimal places. If you go to 2 decimal places, they mark it wrong. So kind of good habit to just go 3 decimal places. This one isn't so nice to work out without a calculator. Right? You get 3 to the negative 4/9. I think if you use the fraction button on this, you don't have to put parentheses around it. But if you use the division bar on my calculators at least, if you do 3 caret negative 4 divided by 9, if you don't put parentheses around that, it'll take it to the negative 4 power and then divide everything by 9. So I think either use the fraction button or just get in the habit of putting parentheses around that. I got 0.614. Did you get that? And remember, I know that you've been rounding for a long time, but just a brief reminder that if you're rounding to the 3rd decimal, then the 4th decimal is what determines whether you round that up or not, right? So just make sure you pay attention to that, because if you wrote 613 here, that's really not rounding correctly to the 3rd decimal. So just be aware of that on your calculations. Right? That's not too bad. They look at a problem like this, and I think they give you one in the homework that's like an XY chart. Maybe they give you one that's even graphed already, and they ask you to write the equation. We did this with parabolas, right? Write an equation that goes through these points for a quadratic function. You've been doing it for linear equations forever. The big thing to remember is use the formula for exponential functions, which is y equals, or f of x equals, a times b to the x. And maybe you could look at this and you could figure out what's happening every time. I'm not really usually very good at doing that, especially if it's a weird number. So I always just plug some points in and see what I can find. The best point to use first is the one that has 0 in it. And if I plug that in, right, these are all just points on my graph. We could sketch them if we want. But I'm just going to plug in the x and the y for that. So y is 12 when x is 0. And you really could have done this for any of them, but it works out the best when you have 0 here, because what's anything to the 0 power? 1. So you just get that a equals 12. If you look back at that first slide, we talked about a is the initial value. Initial value means what you get at the start. So it hopefully makes sense that whenever x is 0, the y value there, like that's going to be your initial value, right? And if you notice that without having to plug it in, you can just plug 12 in there right away, right? The initial value is like where you start, or what would that be? The y-intercept of the graph would be the initial value. So we could say y equals 12 times b to the x. We also have to find out what b is. So now we have 4 other points we can pick. You can pick whichever point you want, and it should work out. But pick the one that's going to be easiest, maybe. Which would be the best value to plug in for x here? What would be a great exponent for us to plug in here? 1 seems like a great choice. But I promise if you pick the other ones, you're going to get the same answer. You just have to do more algebra to solve it. But if I plug in the point 1, 4, I get 4 equals 12 times b to the first, right? So if it's b to the first, I don't have to do any square root or anything. And if I divide by 12, I can get that b equals 1/3. So just like with quadratics, just like with linear equations, you have to solve for the parts that's missing. And then when you go back, you plug that in and you leave x and y in the equation. So we would get 12 times 1/3 to the x power. And maybe you remember from last year or from chemistry class, if this number is a fraction, if it's less than 1, as x is getting bigger, our amount's actually getting smaller, right? So notice at -2 it was 108, and then as x is getting bigger, our number is actually getting smaller because our base there is 1/3, right? If the base was 3, then it's going to keep getting bigger. Something to think about there. Questions about that? Okay. So let's look at some graphs of these to remind ourselves what they look like. I remember from the Algebra 2 book, there were some terrible, terrible exponential graphs in that book, and I don't know why they make you graph those awful things, especially by hand. These are pretty basic, and using the transformations, we can even make them easier to graph. But I just wanted to remind you of the basic shape of an exponential graph. It's one of the ones that was in our little 10 basic graphs that we should know. We did e to the x, not a to the x here. But every time I kind of squish these graphs. I don't know how well they copy for you. But if you wanted to make a little XY chart here, if you just picked a few points, it might come back to you of what the shape of this is supposed to look like. If I picked 1, right, I would just get 2 to the 1, which is 2. If I pick 0, I get 2 to the 0, which is 1. And I don't know that I need to write all these down. You could keep going up. If I pick 2, 2 squared is 4. If I pick 3, 2 to the 3rd is 8. Right? It's just going to keep getting bigger. What happens when I pick negative numbers? What happens when I get 2 to the negative 1? It gets fractions, right? Negative exponent means you move it down. So 2 to the negative 1 really means 1/2. 2 to the negative 2 means 1/4. 2 to the negative 50 means 1/2 to the 50. Am I ever going to get 0 out of this? That's really, really small. And sometimes on your calculator, it might even tell you 0 because it's so small that it can't give you the decimal that goes with it. I think 2 to the 100 it might do that. But when you actually work it out, it's still a really, really small number, not 0, not a negative number, which means we're going to have an asymptote on this, right? An asymptote that doesn't work with our rules of how we've done asymptotes before. So if I graph this, my graph is super small here. At 0, it's at 1. At 1, it's at 2. I'm going to put a few more dots here. At 2, it's at 4. At 3, it's at 8, right? This side is going to just keep going up at a pretty fast rate. 2 to the 5th is 32. 2 to the 6th is 64. So at 6, it's going to be all the way up at 64. But when I go backwards here, I'm just going to keep getting smaller and smaller numbers closer to 0. 1/2, 1/4, 1/8, 1/16. Which means I'm going to have this horizontal asymptote that pretty much just kind of runs into my y-axis. It really never actually gets there, but it gets so small that it almost looks like it touches it. Right? We call that, and we're going to write it out on the next slide, maybe you saw it already. But we say that's exponential growth because it's growing so quickly. Bacteria reproduce exponentially, like they grow very, very rapidly. And then I just do the 3 to the x here to show you that a is just your base, and all it does is it just changes the rate that it's growing. 3 to the x should look pretty close to 2 to the x, where the numbers are going to be a little different, right? If I just picked a few numbers here, like -1, 0, and 1. If I, again, do a negative exponent, it's just a fraction. So that's just 1/3. Anything to the 0 power is 1. And now it's 3 to the 1st instead of 2 to the 1st, which means it's 3. But again, it's that same basic shape that we're looking for. So think about on this one, it's going to grow even faster. At 2, it would be all the way up to 9, right? But this side is still just going to go back and have your horizontal asymptote. 5 to the x would look pretty much just the same. 9 to the x, it just would go up a lot faster. every single one of them, if there's no transformation, is going to touch the y-axis at 1, and they're going to have that horizontal asymptote. And then we'll talk about the transformations of what they would do. What happens when I make it to a negative exponent? What happens when I plug 0 in there? It's still 1, right? 2 to the negative 0 is still just 2 to the 0. What happens when I pick positive numbers now? Yeah, now when you pick positive numbers, you get negative exponent, right? Because that's 2 to the negative 1. So now this side is going to get closer and closer to 0. And what happens when I pick negative numbers? 2 to the negative of negative 1 would be 2 to the 1, which is 2. Which means I think we're taking this graph here and we're just flipping it over the y-axis, right? So now this side is going up, where this side is going down. And if you remember anything about our transformations that we've talked about, if you put a negative up there with the x, or you put a negative inside the function, it flips it over the y-axis. So this is just a reflection in the y-axis. This one we call exponential decay. And when you talk about the half-life stuff in chemistry class, that's what you're talking about, that over time, it's getting smaller and smaller and smaller until it gets to 0, or almost to 0. And then these are exponential growth. We talk about that a lot with bacteria, just any kind of population growth. Usually we can talk about that. So on the next slide, I just kind of gave you some domain range, some basic facts that you should know. Again, if you know what the graph looks like and you know the rules for transformations, you can graph these very quickly and easily and know what's happening to them. So that's kind of why I put the second graph, or the second thing here. We're talking about a being greater than 1. We'll talk tomorrow about how they can trick us. If a is negative and the exponent's negative, like, we have to think about, is it growth or is it decay? What's happening? But if a is a positive number, bigger than 1, then the exponent can determine whether we're talking about exponential growth or exponential decay. On both of these, the domain and range is the same. So let's look back at this. What would the domain be on all 3 of those graphs? All real numbers. You can plug anything you want in there for x. X can be a fraction, x can be a decimal, x can be a positive number, x can be a negative number, x can be anything. And you can see from the graphs that the x goes forever this way, and this way is just going to keep going up. So on both of these, we can say my domain is all real numbers. I'm going to say negative infinity to infinity. And no matter what transformation you do to that, the domain will always stay all real numbers. But the range will never be all real numbers because it stops, right? And on these 3 graphs, the parent graphs, what is the range of all of these graphs? What isn't? What y values aren't you ever going to have? You're never going to have negatives. What else are you never going to have? 0, right? No matter what number you plug in here for x, the y value will never be negative, the y value will never be 0. And you can see that from your graph, that it never gets there. So we want to say that our range is everything positive, right? All positive numbers. So could I say not including 0 to infinity? What would that be in set notation, do you know? Not x, that's for sure. I don't do set notation very often. How would I say everything not including 0 and going up as an inequality? How would you graph this on a number line? How would you say 0 to infinity, not including 0? parentheses on it and shade this way, right? What does that mean as an inequality? How would you write that? No. Right? Y is greater than 0. I'm okay with either notation. I always use interval notation. Some people like set notation, so I try to throw that back in. Just an inequality. The rest of these I think are the same, right? The y-intercept on both growth and decay. When you plug in 0 for x, anything to the 0 power is 1. So your y-intercept is 1. I filled this part in for you. Both of these are continuous functions, right? There's no vertical asymptotes. There's no breaks in it. They're continuous. But on a growth function, right, I'm going to write here, exponential growth, the function is increasing. On exponential decay, the function is decreasing. And you will always have a horizontal asymptote. And if there's no transformation there, right, if it's not moved up or down any, that horizontal asymptote will always be the x-axis, which is what equation? What line is the x-axis? What equals 0? Y equals 0. Right? X equals 0 goes like this. Y equals 0 goes like this. All the transformation rules apply to all functions, which means if you remember, when you add a number outside the function that it moves your graph up and down, then that means it's going to change your horizontal asymptote and your graph's going to move up or down that many. A number inside the function, which means up there in the exponent, is a horizontal shift. It's going to move your graph left and right. A negative is going to reflect your graph. An extra number multiplied in front is going to stretch or shrink your graph, right? All of those same rules apply. XY charts work. But if you know the transformation, it's going to make your life so much easier as you do these. So I stuck with my 2 to the x. 2 to the x is probably the easiest function to graph because you can get so many numbers, right? It's small. 2 squared is 4. 2 to the third is 8. As opposed to if you pick 5, 5 squared is 25, and you have to make your graph really big. I'm going to use lots of colors here. I know you don't have colors, but I'm going to label them f of x, h of x, g of x, k of x, just to show you here what we could do. So 2 to the x. We already graphed it, so I'm not going to spend a lot of time on this. I'm just going to graph my numbers that I know. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 to the third is 8. 2 to the negative 1 is 1/2. Right, so I can graph this. And I just wanted to do this to kind of show you the transformations that you don't have to do a lot of work, and I can actually show you some shortcuts of how to pick the numbers here. Questions on this one? On the f of x? So if I do h of x, right, if you're not sure what's going to happen, you can always pick points. If I plug, what does a negative mean for us transformation-wise out front? Do you remember? A reflection in the x-axis. Think about x squared, right? If it's x squared, it opens up, but if it's negative x squared, it opens down. So this means it's going to take this and it's going to flip it over. Sometimes that really throws people off when they pick numbers here, because if they pick 0 for x, people want to say that you still get 1 for y, but when it's written like this, if you type that in your calculator, I think it will get you, does it give you -1? Because your calculator, right, it does negative, and then it's doing 2 to the 0. So order of operations, it's doing the exponent, and the negative is kind of out in front of the 2. So it's almost like there's a -1 times that. So it's like you're going to take all your answers and multiply by -1. That's why if you just know the transformation that you flip it over, you don't even have to pick the points here. If you picked 1, 2 to the 1 is still 2, but then you have the negative in front, right? So if you know that, you can just take this graph and flip it over. So this is now going to be a -1, -2, -4, -8, -1/2. And now you still have that same horizontal asymptote at y equals 0, but notice that your range has now switched from 0 to infinity, from -infinity to 0, right? So now we're talking about the negative y values are what we're getting. That would be h of x. And remember what it means when you add or subtract a number inside the function. And for an exponential function, inside the function is going to be up here in the exponent. It means a horizontal shift. So this means that this has moved which direction? Plus 1 mean for horizontal. Does that mean right one or left one? You tell me, is that inside the function or outside the function? One of these is inside, one of these is outside. Inside, right? So up in the exponent is inside. So which directions are going to be? Left, because it's the opposite of what you normally think. If you know that it's left 1 unit and you know what the paragraph looks like, you can just move it over. If you don't know and you need to make an XY chart, my advice to you is pick what makes that exponent go to 0, pick one above it and pick one below it, and you'll always get a decent graph. What do I mean by that? Normally I pick 0 for my exponent, but if there's something added there, the first number that I would pick would be -1, because -1 plus 1 gives me that exponent of 0. 2 to the 0 is 1. And if you pick one above it and one below that number, then you should get that shape of your graph. You should get like these 3 points here. So if I picked 0, I would get 2 to the 1, which is 2. And if I picked -2, -2 plus 1 is -1, which gives me my 1/2. Or I get 1 over a, 1, and a, where a is my base. So if you get stuck, that's my advice to you, is pick what makes your exponent go to 0, go 1 less than that and 1 more than that, if you don't remember what happens when you do that. It's going to kind of overlap here a little bit, but at -2, this one was going to be 1/2. This would be up to 1. This would be up to 2. This would be up to 4. So we've just shifted it over. It's still growing. It's just a little bit off now from the other one, right? Which is hard to do when you don't have colored pencils or something to show that on your graph. And then the last one really quick, what does it mean when you add or subtract a number outside the function? Yes, and since it's +3, we know that that means it's moved up 3. Probably this is the one that I see the most mistakes on, because we get so used to having that asymptote on the x-axis. If you move up 3, your asymptote has also moved up 3, right? So if you made a chart here, and you picked your points, 2 to the 0 is 1, but then we're adding 3 to that. So now we're up to 4. 2 to the 1 is 2 plus 3, so that goes up to 5. And when I plug -1 in, I still get a 1/2 plus 3, which means 3.5. So think about that this is going to get closer and closer to 0, but you're always going to add 3. So if it helps you, draw a little dotted line through the line where your asymptote is, so you remember that your graph doesn't go below that, okay? So this would be my -1, 4, 5. Don't do this, but what I see happening is people do this, and then they go like this, and they make their line go way down, which is going to be minus a lot of points for you. on a test, because the biggest thing I want you to get out of this, besides the shape, is that you recognize what the domain and the range are. You recognize that there's an asymptote, and on this one, that graph can never cross 3 on the y-axis. So my line has shifted up 3, and then this side, we're just going to go from there. So it doesn't have to be perfect, but what has to be perfect is your asymptote. You have to make sure that you either draw that in or know that you don't make that go below there. Questions about that? Also, last year you learned about E, all right? E is a number just like pi, but E doesn't get as much attention as pi because you learned about pi way back in, like, I don't even know what grade you learned about pi. 6th grade? When do you learn about area of the circle? Definitely middle school. You have to talk about pi because you talk about the area of the circle. You don't have to talk about E until you talk about logarithms, but E probably has just as much importance in the world of math that pi does. So E is an irrational number just like pi. So instead of using the Greek letter pi, the pi symbol, we use just E. And E has tons of applications with science and interest and population, lots of applications. Probably comes up more outside in real life than just regular exponential functions do. There's a button on your calculator for E, but those are the first few decimals. Why don't we have E Day on February 7th? I don't know, but there's no good E songs. On your calculator, at least on my calculators, if you hit the E button, it automatically takes it to a power, like it says E to the, and so on my calculator, you'd have to hit 1 in order to get that approximation. We call E the natural exponential function, and maybe you already remember the natural logarithmic function that goes with it. Euler is the one that got credit for the E function. I always say that's why we call it E, but I don't really know. I'm just making that up. But Leonard Euler did a ton of stuff with E, and he's the one that gets credit for discovering most of it. Someone asked me once, where does E come from? Pi comes from dividing a circle's circumference divided by its diameter. So where does E come from? If you add up all these, right? How do you add up something that goes on forever? That's chapter 9, we'll get there. But if you add these up and you keep going, right, so plus 1 over 4 factorial plus 1 over 5 factorial, and you keep going and you add that up, you get this digit, because this is just going to keep getting smaller and smaller and smaller as you go. And again, look at that word limit that's in there. They say that E is the limit of adding up this as it tends to infinity. And Euler, way back in like the 1400s, found E to approximation of 18 decimal places. That's without a calculator. That's without technology. Figure that out. So that's why he gets credit for natural exponential function. Today, what are they going to have you do? They're going to have you use your calculator. So they're going to say evaluate E to the second power, which is just using your calculator. And again, rounding to the second, rounding to the third decimal place. On my calculator, if I hit E squared, I get approximately 7.389. What if they ask you to graph E? That's so fun, right? You just need a calculator, so to graph E, you just have to take numbers, and you're just going to get a decimal. Do I have a graph on here? I don't, do I? What's E to the 0 going to be? Still 1, right? So if they give you something to graph with E in it, it just means you need a calculator. So scientific calculator, hopefully maybe you have one. If you don't, if you have a phone, you have a calculator with the E button on it. My calculator on my phone, I just have to turn my phone sideways to get it. If you have a computer, then there's a calculator on it with E on it. Or you can just Google free calculator or online calculator, and you could find one to do that. Or if you have a study hall and you need to borrow my calculator for study hall, just come and let me know, and then bring it back after study hall so that I can get it. But if I plugged 0 in there, I'm still just going to get 1. If I plugged 1 in there, I'm going to get E. There's no E on my number line, but you can use your calculator, or you can use what we just said that said E is like 2.7 something. So I'm going to say about right there. If I plugged -1 in, it would be 1 over E, which again, I'm just going to use my calculator. And it would be like, not very pretty, 0.4. Which means I still know it's going to be that same shape. I could still do transformations with it and just use a calculator to get the decimal answers. People always get thrown off because we don't graph with decimals that often. Just round as close as you can, graph as close as you can, and don't be too thrown off by graphing with E. Questions about that? E is super important because of ln. Right? All right, I think that's my last example, right? Oh look, I had this, but I think I'm gonna get it. Oh my goodness. How about this one? Let's look at this one before I let you start. It says, describe how to transform the graph of f of x equals e to the x into the graph of g of x equals negative e to the negative x plus 2. There's a whole lot of transformations going on in that. So don't say it out loud, but think about that and think about which choice that would be. And we'll hold up fingers in a minute, like A, B, C, D, what all would be happening on that problem. You got your answer yet? And at least do process elimination, right? The plus 2 should help you at least get down to a 50-50 choice there. All right, let's see what you got. A, B, C, D. What do you think? So what's the plus 2 mean? So the plus 2 is outside the function, right? It's not up there with the x, so I think that means vertical, right? So that should mean up to. So not this one, not this one. And then there's 2 more things happening, right? There's a negative out front, and there's a negative up there. So I think I agree with the 4s there. I think that's reflected in the x-axis, and reflected in the y-axis, and moved up 2. Sometimes when there's a lot of stuff like that happening, it gets really weird to graph it. My advice is pick some points, make an XY chart to help yourself if you're not a really visual person to do that. There should still always be a horizontal asymptote when you're doing these problems, okay? Okay. I don't have a new assignment sheet for you, but I'll work on getting you one for tomorrow or Wednesday. Here's your homework, 1 through 13 odd, 15 through 30 multiples of 3 and 39. Is an exponential function, evaluated using a calculator, and then there are some graphing ones, or just, yeah, definitely some graphing ones. I do. Button, and push L right there. So you have to do backwards though, right? So you would do like 2 seconds that. So you hit your exponent first, second, and then ln. Alright, so yeah, let me get graph paper.